Welcome to the fourth lecture of the fourth week of the course in machine learning. In this lecture we will talk about instance-based learning. For practical reasons, this lecture is divided into two videos, and this is part one. The subtopics of this lecture are as follows. First, I will talk in general about instance-based learning, what it is, and say a few words also about the character of the so-called instance space. Then we look in more detail on a particular algorithm called the k-nearest neighbor algorithm, and in conjunction with that discuss an important aspect of this kind of systems, the distance and similarity matrices. And then we will expand and look at a more general neighbor, k-nearest neighbor algorithm called the weighted nearest neighbor. After that, we will go into a kind of different area. We will talk about support vector machines, which is a kind of binary linear classifier system, and I will talk about something called kernel methods, where kernel methods is useful in order to make machine learning algorithms that basically handles the linear case, also being able to handle the non-linear cases. Instance-based learning is a family of learning algorithms that instead of performing explicit generalization, compares new problem instances with instances seen in training, which have been stored in memory. As a consequence of that, this kind of technique is also often called memory-based learning. The reason for the name instance-based learning is because this kind of technique evaluates efficacy directly based on the training instances themselves, and not explicitly towards a built-up hypothesis. One can say that instance-based learning is a kind of lazy learning, where the evaluation is only approximated locally and all computation is deferred until classification. There is no computation needed to build up hypothesis, obviously. In the worst case, a hypothesis is a list of n training items, so therefore the computational complexity of classifying a single items is at least of the order of n. One advantage that instance-based learning has over other methods in machine learning is its flexibility to adapt its model to previously unseen data, because actually the character of its classification change with a build-up of the memory of instances. And an instance-based learner may store new instances and or throw away instances. It depends, of course, on the details of the algorithm. In many machine learning approaches, the internal structure of the instance space is not explicitly considered. However, the character of instance space is always important. It will always implicitly influence the performance of learning algorithms, even if the character of the instance space is not explicitly considered in the algorithm design. But here, in contrast, for instance-based learning, the character of the instance space is of key importance. In earlier lectures, a few crucial aspects of the instance space have been mentioned. The number of features, the value set of features, instances with special status. We talked about prototypes, outliers, and near misses, which are all structural aspects. Also, we mentioned similarity of distance measures, which is a key issue here. But we will also now talk about structural properties of the whole space, such as sparseness, density, etc. These aspects will now all come into play. I will now concentrate the discussion on one particular kind of instance-based learning algorithm called the k-nearest neighbor algorithm, KNN. In this algorithm, the analysis is based on the k closest training examples in the instance space. What I mean by closest is closest to the query item. K is a predefined positive integer that have to be set before you use this kind of method. Normally you choose k to be small and odd. Potentially, an optimal k can be calculated by a special technique, hyperparameter optimization techniques. So, as you may have understood by now, many of these parameters can also be learned. The parameters control a learning technique, but the parameters themselves can be learned through special techniques. So this is a second order kind of learning that is possible. However, the typical representation of an instance here in this case is a feature vector with a number of attributes or features plus a labeled plus a label or a number which constitutes the target function. We still here talk about supervised learning. So we still suppose that all our instances are labeled. The training phase is simply the storage of the feature vectors of all training in a data structure. Nothing more happens at that point. For this kind of approach, we only need a distance metric. That means a metric that measures the distance between the instances. The default metric is Euclidean distance, the well-known distance. It's the distance between two elements in an Euclidean space, the square root of the sum of the differences between the Euclidean coordinates of the two elements. Normally, also you select and define a metric like this one, but also, as for the number k, the metric can also be learned hypothetically. The KN algorithm can be used both for classification or regression, and in the KNN classification case, the output is of course a class membership. Here a query instance is assigned the class label most common among its k nearest neighbors. If k is equal to 1, of course, then it's, which is a special case, then the instance is simply assigned the class of that single nearest neighbor. And one can say, in a way, using an analogy, that all the k nearest neighbors vote for the choice of the class label in the case of k being larger than 1. In KNN regression, the output is the property value for the query instance. This value is the average of the values of its k nearest neighbors. For examples, for practical reasons, we will use the simplest case, which is binary classification in a feature space of 2 dimensions. So to the right, you can see just a summary of the stages in this kind of algorithm. You look at the data, store them in space, calculate the distances, find the appropriate number of neighbors, and given that you have chosen the neighbors, you calculate the average of the outcome and take that as the class label in this particular case in a classification task. On this slide, you can see a very simple illustration of a classification application for the k-nearest neighbor algorithm. It illustrates the outcome of the algorithm for different values of k. In this case, value 1, 3, and 5. So as you can see for the inner circle, there is you only look at the closest neighbor, which in this case happened to be an instance classified as blue. And when you select the number 3, you consider 3 neighbors, and then it happens to be that two more red instances come into play, so the outcome of the algorithm will be red. While if you consider 5 instances, 2 more blue come into play, so then suddenly it weights over again towards the blue case, so the outcome of the algorithm will be blue. So this shows that the outcome of this algorithm will change, clearly change, depending on how many instances you include in the process. It's obvious that in the case of instance-based learning, there is only one explicit space, the instance space. As been said, a hypothesis space is never explicitly built up. One can say that the hypotheses are implicit in the structure of the instance space as defined by the chosen metrics. One form of illustration for these implicit representations is the so-called Voronoi diagram. A Voronoi diagram is a partitioning of the decision surface into convex, polyhedral surroundings of the training instances. Each polyhedron covers the potential query instances possibly determined by a training instance. Query points out that it specifically is closer to another training instance and is of course also included in some polyhedron. This kind of diagram is not explicitly used for the processing of the algorithm, but it shows an important purpose in being able to illustrate for the user of the system how the situation looks like. And we exemplify here all the time by two-dimensional cases, but as you understand, it's natural to extend this kind of technique to dimensions larger than 2. So you can see at the bottom to the right an illustration of that case. One important feature of or aspect of instance-based learning is the existence of a distance measure, similarity measure, or proximity measure. And you have always to define this kind of measure for the instance, all instances in the instance space. And as you can see from the figure to the right here, this means that the instance space always have to be a metric space. This means a space with a metric. However, the most typical case is that our instances are feature vectors. It doesn't necessarily have to be so, because an instance could be anything, and you can also think of other kind of entities on which you apply some metric. But the very, very common case is of each vector. So therefore I want to talk a little on this slide about two kinds of vector spaces that are well known from mathematics. It's called a normed space and an inner product space. So the more general category is a kind of vector space that has something called a norm. So a norm is a real valued function that intuitively is coupled to a length or a distance. And a norm satisfies a number of key properties. One of them is number 4 here, is a triangular inequality. This means that the distance is the norm of two vectors is always less or equal to the sum of the norms for each one of them. We have a special notation for the very special case of a Euclidean norm. The Euclidean norm is actually a norm, the traditional norm we know of from a Cartesian space, where the distance is the square root of the square root of the sum of the arguments or features of the vector. Obviously, a distance here naturally is the norm of one vector minus the other. So this is normed space. Then we can go further, and we can look at a normed space where there also exists an operation called the inner product. And as you can see down there, an inner product or dot product in the Euclidean case called also they are equivalent. Can be is first of all a scalar value, and also the classical definition is that the inner product of two vectors are the product of the norm multiplied by the cosine of the angle between the vectors. And as a special case, when the angle is 90 degrees, the cosine becomes 0. So then the inner becomes also products as a consequence. And we call this in this case the two vectors are orthogonal, and that's the terminology. So we need these concepts because when we define distance measures, we need both the concept of norm and we need also, in some cases, the concept of inner product. And you can see in the picture to the right, an inner product space is a subset of the norm vector spaces, and non-vector spaces is a subset of the metric spaces. Let's turn then into distance and similarity matrices. So a distance metric, distance measure, distance function are synonyms, is typically a real valued function that quantifies a distance between two objects. So distance between a point and itself are 0. Of course, all other distances are larger than 0. Distances are symmetric, and then we have a triangle inequality, which informally means that detours cannot shorten the distance. So it's always longer to go from one point to another by another point. So distance metrics, similarity metrics have been developed more or less independently. So in certain cases, it's more practical to talk about the distance between one vector and another, or one point and another. In other cases, it's more natural to talk about how similar are things. So therefore, depending on the context, these people have developed on one side distance metrics, on one side similarity metrics. But obviously, they're always connected intuitively. And obviously, they are somehow inverses of each other and can be transformed into each other. But you will find, and maybe it's a little confusing, that sometimes talk about distance metrics separately and similarity metrics, and they define them separately. But of course, there can always be a transformation between them. So typically, similarity metrics takes values in the range of -1 to 1. So they are always normed somehow, where 1 means that the objects are regarded as identical, and -1 is the maximum distance considered by the. So if you have a similarity of -1, these objects are as far from us as you can think of in that context. While distance metric often take values from 0 to infinity or anything. But of course, there is always then some transforms and normalizations to be made to make distance and similarity matrix comparable. We will always here exemplify by using metrics in a normed Euclidean vector space. The matrix is based on overlapping elements. So those are the two cases we will focus on. I now want to give you some examples of distance measures. So first we start with a category which is called here norm metrics in normed and inner product vector spaces. So these are the kind of classical measures suitable for instance spaces where we have normal feature vectors. And there is something called a Minkowski distance, which is maybe not so well known to you. But one can say that the Minkowski distance is defined in such a way that it has become an umbrella concept for three more well-known types of distances. So actually, Minkowski distance is defined as you take the sum of the differences between arguments for two vectors. You raise each sum to the degree of k. You make the summation, and then you take the kth root out of that sum. And when one then looks at different values of k, you can see that if you take the value k, you get your Euclidean distance. So then you get simply the sum of the squares of the differences, and then you take the square root out of that sum, the classical theorem of Pythagoras as a distance. So that's well known. If you take the k as number 1, you get something else that is also pretty well known called the Manhattan distance. And actually, the Manhattan distance is then the sum of the absolute differences of the argument differences. And it's called Manhattan distance because if you consider you are moving around from one office to another in Manhattan, the most important thing is not the distance on the ground, it's also the distance in the houses. So you go from the 100th floor in one building to the 250th floor in another. It's more important with the vertical distance than the horizontal. So that's like a little joke called this the Manhattan distance. Then we have a third case. This is also rather well known, that if we choose the value k to be infinity, and then the formula deteriorates. So actually, in this limit of infinity, we get actually the definition of the distance as the maximum value of the differences in arguments. This distance is also called the chessboard distance because actually this is equivalent to the to the minimum number of moves a king can make on between two chess points. A special measure I want to mention that not only needs norms but also needs inner product is the cosine similarity measure. So actually the cosine similarity measure is equal to the cosine of the angle between the two vectors, and that can also be calculated then as an equation in terms of square roots. It's interesting because in some cases when we compare feature vectors, the size, the length of the vectors are not necessarily important, but rather the angle between them. Of course, it's a little abstract here because if we have a feature vector and another feature vector, what does an angle mean? But there are obviously some domains where it makes sense primarily to look at the difference in angle, and that's exactly what this measure measures. So obviously, these algorithms get very different property depending on which similarity metrics you apply. So if you have a system, a nice system where you can simulate these and you can easily produce Voronoi diagonal visualization, you can then easily see that when you plug in one matrix, you get one result, and when you change, you get a different. So here you can see an illustration how you can how the Voronoi diagrams looks when you apply an Euclidean matrix on an application, and then what you get when you change to Manhattan distance, for example. Some of the similarity measures are pretty straightforward and easy to understand, but maybe the use of the cosine similarity is a little more unintuitive. So to give you an illustration of the use of the cosine similarity, I included an example here which I find pretty neat. It also shows, actually it's a simple example, that in many applications you have to map properties of instances in a domain that is a rather different form into a kind of feature vector. So this is an example of a domain where you want to look at medical texts or pharmaceutical texts or medical texts, and you want to measure the frequency of certain kinds of terms. So the trick here is you take each text fragment or page or whatever is the unit of analysis, and then you count the number of the key terms you want to measure. And then you choose as features or dimensions of your instance these terms. And the values of each such term becomes the frequency of that term in that particular text. So this shows how you can take like a normal text, and the page is of course the kind of raw instance data, and then you transform that text into this feature vector that just keeps the key terms and the frequencies. So then when you transformed the instances of that domain into a feature space, then you can apply this kind of methods. And then also intuitively, it makes sense that it's the relation here of frequency. It's not so important with the actual number. It's more important to see, is it one term that dominates over the other? So intuitively, I hope you can understand that the differences, then the distance between these are more of the angle between the vectors, because the angle is influenced by the relative size in the different dimensions. So therefore, this is a case where the cosine matrix makes sense. Metrics for feature vector spaces are important, but not necessarily we have to be tied to that. So sometimes it could be so that our instances are something else. So our instances could be sets, binary strings, text, and so on. That's possible. So therefore, I included here 3 examples of similarity measures that works on that kind of instances. So if we look at texts or words, we have something called the Levenstein distance, which actually embodies the idea of changes or substitutions that have to be made of single characters in the text or word in order to create the other. So Levenstein is an example how you can define a similarity matrix or distance matrix between text. Similarly, if the instances are sets, then we have something called the Jacquard index, which measures actually then similarity between finite sets, and it's defined as the intersection of the two sets divided by the union. The final example is something called Hamming distance, which is a classical distance from information theory, where you actually, it's very similar, of course, to the Levenstein distance, but it's defined for binary strings. So actually, the Hamming distance is the number of positions at which the corresponding symbols are differences. So it measures the number of minimum substitution required to make the two strings equivalent. Going back to the k-nearest neighbor algorithm, I just want to mention before we leave it some issues that one have to consider for this kind of algorithm. So actually, theoretically, the number k can be anything, but typically one should avoid an odd number to avoid tied votes. Very practical comment. And either you define k yourself, or you can try to learn it. And in the next slide, we exemplify a kind of method, which is also a kind of learning method, how one can define or infer a suitable value of k through something called the Bootstrap method. Another comment is that this kind of majority voting for deciding that can be problematic when the distribution is skewed. So of course this method is also dependent on how the instances are distributed in the instance space. Also, if you have a very large number of examples of one class and very few of another, it also can create an issue because of the density of the dominating class can happen to be high in the context of a new example. So this can also create anomalies in the analysis. Also, if you have a large feature set and with where you haven't really done a thorough feature engineering, many of these features can be irrelevant, and therefore the instance space expressed in these features can have strange properties of balance. The relevant instances may be in one corner and irrelevant in another. So this may also cause problems Relating to that, you can actually get a very sparse instance space. And it may be so that this idea to have exactly the same distance metric for every case may have negative. So, of course, there are positive things with the k-near neighbor, but as you have understood from this slide, there are also a number of issues that can occur because the structural properties of the instance space can be skewed in many ways. So, last slide I mentioned a method to maybe define optimal values of some of these parameters or hyperparameters needed to be set for an algorithm like the k-near neighbor one. And one such method is called the Bootstrap method. And this method works in such a way that one takes small samples out of the original data set, and you draw observations from the large sample one at a time, returning them, of course, because you won't disturb the data set. After this process, the data set has to be as it was. So this method allows you to use observations for a pre-study, and then you can, as if nothing happened, you can then continue in the end with the original analysis. It's called sampling with replacement. So the Bootstrap method can be used to estimate the quantity of the population. So you repeatedly take small samples, calculate whatever statistics you want. So in our case, the last slide, you try to calculate a prognosis for a good K, then take the average of the calculated statistics. So to summarize, in the Bootstrap method, you choose a number of such samples, you choose the size of the sample, and you draw a sample with a replacement, you calculate the statistics, and then you take the calculated mean of the statistics. Of course, you have to be as precise. This is a general method, so you have to define, of course, a precise measure for calculating the statistics you're interested in. But it's a general scheme for making pre-studies, so to say, of a data size, data set in order to get a good prognosis for the setting of a hyperparameter. For practical reason, not to make the video too long, we make a break here, and we continue to talk about instance-based learning in part 2. Thank you. Bye.